Hello, and welcome to the lecture for Chapter 5 on the topic of radiation and spectra from OpenStax astronomy. This chapter is very much a crash course in modern physics, specifically the modern physics we need to understand a little bit about astronomy. This chapter combines well with Chapter 3, which was all about the classical laws of mechanics, namely Newton's laws and Kepler's laws, and the conservation laws of energy momentum. But here we're going to be talking about different laws altogether. So let's take a look at what's going on with modern physics as it applies to astronomy. Okay, well, as the title of the chapter implies, radiation and spectra, we're going to be talking about light. Well, I hope it implies that, and it will certainly by the end, because when we talk about radiation, that's another name for light. When we talk about spectra, that's how we understand light. And indeed, here is a beautiful example of understanding light, specifically light that is invisible to the human eye, which would be, in this case, I was almost going to write IV, but we should write UV, ultraviolet, all right? Ultraviolet light known as UV light. We cannot see this light with our eyes. Our eyes did not evolve to see this type of light, but we can use certain types of digital sensors to see this type of light. And then we can code this light to colors that the human eye can see, like red and oranges and blues, to represent different types of UV light, because there's more than one type of UV light. And what we're looking at here is our own sun, but not the visible light that's produced by our own sun, but instead the UV light. And one thing about UV light is it's higher energy than the type of light that we see, the visible light. And we'll come back to this idea. But this is amazing that we can see the sun in other ways. We don't just have to see the sun as a glowing yellow ball in the sky, nor do we have to see it as a white ball in the sky if we were in outer space, because the sun appears as white outside of the atmosphere and it appears as yellow within the atmosphere. And that's all due to the effects of light, okay? But it's not just producing those colors of white or the yellow that passes through our atmosphere. It's actually producing lots of different types of light. So, light itself was first understood at the end of the 19th century by a number of scientists, but most famously James Maxwell. And what James Maxwell did is combine electricity and magnetism and the theories of electricity and magnetism to unite them into light, which is really a mind-bogglingly big theory. And we're not going to present any equations here of Maxwell's famous equations, because there are a set of four equations which are known as Maxwell's equations and really completely describe all of electricity and magnetism within those four equations. Instead, we're going to present some simpler equations throughout the chapter that apply to some particular cases of light. But let's just stop and appreciate this. Electricity is, well, what we'd exactly expect. This is the electricity that flows through wires, that comes out of outlets in your homes, the electricity in electrical circuits. Well, that phenomenon of electricity combined with magnetism, like the magnets that you stick to your refrigerator, create light. Electricity and magnetism and the interaction of the two create light. In fact, electricity and magnetism are not separate phenomenon. Electricity creates magnetism, magnetism creates light. And that process of one creating the other is in fact light itself. The big idea here is that any time a charge, we'll say charged particle, is accelerated, light is created, or you could say produced, okay? That's so important because the most common type of charged particle are electrons. Electrons are what flow through wires. And whenever those electrons are accelerated, which means they're slowed down or sped up or even just turned, because turning is a form of acceleration, light is produced. So that means that on the microscopic level, every time electrons bounce around within molecules, light is produced. Every time electrons move within atoms, within different energy levels of those atoms, light is produced. And by the way, that idea of energy levels within atoms, we'll be talking more about that in just a minute. Because although this chapter is titled Radiation and Spectrum, we're also going to break down some important facts about the nature of atoms themselves, because we really can't understand one of the biggest ways that light is produced without talking a little bit about atoms and the structure of atoms, okay? But this is all made possible by an understanding of Maxwell's equations, and anytime a charged particle is accelerated, light is produced. So in other words, there's a lot of ways that light is produced, okay? Now, light is a wave. Okay, it's also a particle, and we'll come back to that idea in a minute. But light is a wave, just like the ripples in this pond are a wave. This frog splashes within the pond, creating an effect of ripples spreading out through the pond. The analogy here is if we had an accelerating electron within space itself, well, that would create ripples of electromagnetic phenomenon called light. Okay, so just like splashing in a pond creates mechanical ripples in the pond, waves, so does an accelerating electron create ripples in space, which we call light. Okay, so light is a wave. Light is a wave. And if light is a wave, then it has a wavelength. This is so important that light has a wavelength. It's so important for understanding what light is. It's one of the biggest equations we're going to use is understanding the wavelength of light. And we have a variable, a letter that we use for wavelengths, and this would apply to mechanical waves. And by we, I mean physicists and astronomers. We have the letter that's used, it's a Greek letter, is lambda, which is drawn like this, okay? And it's called lambda. Oh, that's an A. So lambda is the letter that represents wavelength. Wavelength is measured in meters. Now, wavelengths for lights are usually going to be on the order of nanometers, okay, nm. A nanometer is equal to 10 to the negative 9 meters, because light is really short, the wavelengths are, okay? That's a billionth of a meter. So we're talking tiny lengths, although quite a bit larger than atoms, interestingly enough, at least visible light, although there are other forms of light that have shorter wavelengths than 10 to the negative 9 meters, okay? But here's the thing. In addition to having a wavelength, light also has a frequency, okay? Because and there's a wavelength, by the way, any wave has a frequency, and that's how much time it takes to go from a crest back to a crest. All right, the time, in other words, for the wave to oscillate down and then back up is the frequency. It's the frequency of the wave sloshing up and down, okay? So frequency is measured in inverse seconds. The actual time would be the period, the time to go up from the top, back down to the bottom, back to the top. So the time is called the period, but we don't care so much about the period, and the period would just be measured in seconds. Instead, we care about how many times the wave goes from crest back to crest per second, and that's frequency. Okay, so frequency has units of 1/seconds, which are called hertz. Okay, but it's just how many times per second the wave bounces up and down, which is called oscillations. So how many times it oscillates up and down per second. The oscillations for visible light are going to be on the order of 10 to the 15 hertz. So they oscillate up and down thousands of trillions of times per second. So really fast, right? Their wavelengths are fairly small, right, in the scheme of things, because they're actually usually on the order of hundreds of nanometers, but their oscillations are unbelievably fast, okay? Now, here's the interesting thing about that, is that with a traditional wave, like the mechanical wave in a pond, we say that the velocity of the wave is equal to the wavelength times the frequency, which makes a lot of sense, because if you look at it, wavelength has units of meters, recall, right, because it's just a length. Frequency is per second, so look what we got, meters per second, distance over time. Well, that's a velocity, right? If you're moving through distance over time, that's speed, that's velocity, meters per second. So any wave, a sound wave, ripples in the pond are always going to be described by that formula, V equals lambda times F. But here's the special thing about light. Light, according to Maxwell's equations, has one particular speed. Okay? Now, Einstein later showed that that speed never varies, but the speed was first proposed by Maxwell. And that speed is c. Okay? The speed of light. Speed of light. And it is 3, we'll put it up here, 3 times 10 to the 8 meters per second, which is 300 million meters per second. Okay, again, really fast. Light moves fast. It still takes significant time to travel between the stars because the distance between the stars is incredibly vast. We've already started touching on the idea of light years. That's how long that's how far it takes light to travel in 1 year. Okay, or I guess a better way to say that is light travels 1 light year in a year. All right, so that's, light travels at this incredibly fast speed of 300 million meters per second. If we let it continue to travel for a full calendar year, an Earth year, then it's traveled that distance, about 9 trillion kilometers. And that's how far it travels in 1 year. So a light year, of course, is a measure of distance. All right, but here's the actual speed of light. But that number never varies. That means we can rewrite this equation of V equals lambda F, because ripples in a pond do vary in speed depending on the characteristics of the pond and so on, right? And ripples in air travel at different speeds than ripples in water and so on, right? Earthquakes or ripples in the earth, they travel at a different speed, but light always travels at the same speed. So we write the formula as c, the unchanging speed of light, equals the wavelength times the frequency. Right? This is a very, very big equation in understanding light, because it is so useful, because if you know the frequency of light, then you automatically know the wavelength, and vice versa. Since c is an unchanging constant, it allows you to go back and forth between wavelength and frequency. All right, so very, very useful equation, very big idea in understanding light. Okay, well, here's another big idea in understanding light, because yes, light is a wave. And like all waves, even mechanical waves like sound waves and earthquakes, it carries energy. Now, interestingly, light is the only type of wave that can carry energy through the vacuum of space. Mechanical waves can't travel through a vacuum because they have nothing to actually travel with. They require a medium, like ground or a fluid like air or water. But light can travel through a vacuum. It doesn't need anything. It creates its own self-propagation, we say, okay? But besides that little tangent, we just need to understand it travels through a vacuum. But in doing so, it carries energy, okay? Now, how does it carry energy? Well, it carries energy in something that we quantify as intensity. So intensity is a pretty simple idea. It's just power per area, okay? So power per area. And it's the way we tend to think about energy spreading out from a source, like say, a star or the sun, right? Because that's a source of energy. As that energy spreads out from the sun, it's carrying power, which is going to have units of watts, all right? Just like when you talk about the wattage of a motor, for example, all right? A horsepower is 750 watts, for example. Light bulbs might be 10 watts, right? This is the way we typically quantify energy per time. Okay, watts, power, all right? And then area is just square meters, right? So the units of intensity are watts per square meter. So the interesting thing about spreading out through space is when you have the initial source of energy, for example, the sun, well, as that energy spreads out in all directions, it's spreading out over the surface area of a sphere. And that creates what's called an inverse square law relationship. There is less intensity the further out you get. And as you double the distance, the intensity falls off as the square of the distance. Why? Because the area is the area of this giant sphere that the energy is now spreading out over in all directions, three-dimensionally into space. All right? So what that means is that it has that proportionality to area, and area is square meters. Okay? So that means if you have some distance, we call it d, then if you double d over here, so you have 2d, you have twice the distance to where you made your first intensity measurement, the intensity at that distance twice as far away will be 1/4 as strong. Okay, so here we could call this intensity 1 at a distance of d, just some arbitrary choice, right? It could be 1,000,000 kilometers, right? It could be 1 astronomical unit, whatever we decide is our initial distance d. But when we've doubled it, now our intensity is that initial intensity divided by 4. Not divided by 2, but divided by 4. Why? Because of that square relationship. All right, we say that intensity is proportional to 1 over the distance squared. We could also say the intensity is proportional to 1 over the radius squared, because we often talk about the radius of that imaginary circle, that sphere. It's really a sphere, not a circle, but that sphere that the energy is spreading out over. That could be R1, this could be R2, okay? So that's the idea. As you get further away from a source of energy, a source of light, again, the only energy that can spread through the vacuum of space, so the one we care about in astronomy, all right, the energy per area, the intensity, falls off as the square of distance. All right, so that's a big deal because that means that energy falls off fairly quickly. Because it's going with the square of distance, it is decreasing quicker than, say, if it was just falling off with just distance in a linear sense. All right, so that's the inverse square law applies to the propagation of energy through light. Okay, so far we've got that light is a wave, and we've got how the energy that wave carries with it falls off with distance or decreases with distance, right? So big ideas. There are a lot of big ideas about light here, okay? Well, now let's bring this back home to Earth and talk about some maybe more practical understanding of what light we see here on Earth, okay? So I'm zooming in on this image. So here we have what's known as the entire electromagnetic spectrum. All right, so we call this the EM spectrum. Now, you will hopefully not be surprised to learn that the electromagnetic spectrum is the light spectrum. Why is that? Well, Maxwell showed that light is an electromagnetic phenomenon, so EM and light are interchangeable terms. When we say light, when we say EM, it's the same thing. I know it's a little confusing at first, but EM and light are two names for the same thing, okay? Now, often when we talk about light in everyday speech, we're talking about visible light, because this is the light that our particular eyes, the organs of our eyes, as mammals have evolved to see, okay? Now, it's no coincidence that we evolved on the surface of Earth to see visible light, because visible light is the most intense and most common type of light that passes through our atmosphere. And let's see how this figure tells us that, okay? So we have the entire EM spectrum, visible light, right in the middle, all right? And then we have the idea that down on the surface of Earth, maybe where a little person is standing, all right? We're at the bottom of something called the troposphere. The troposphere is the part of the atmosphere that's breathable. It's the part that has clouds and creates weather. Well, visible light passes all the way down to the surface of the Earth through the troposphere. That particular type of light is able to penetrate the particular gases that make up our atmosphere. All right. Now, there's also some ultraviolet light that penetrates all the way to the ground, and there's also some infrared. All right. So UV for ultraviolet because it's more violet than violet, and infrared for red light that is more red than red. Both infrared light and UV light are invisible to the human eye. There are other animals, some mammals, but lots of crustaceans and insects that have evolved to see both UV or UV and infrared, right? One or the other, sometimes both, depending on their surroundings and their particular biological niche. All right, but here's the thing, we can't. We cannot see with our eyes UV light or IR light, infrared light, all right? Now, we use infrared light for lots of applications like TV remote controls. We don't use UV light too much, but we can use it to dry certain types of glue. But UV light is harmful. That's what actually burns you with sunburns, and it passes through the atmosphere, so we have to be aware of its existence, right? Certain days it's more intense than others, okay? But there are certain types of UV light that would be even more harmful that luckily do not pass through the atmosphere. They get absorbed in the atmosphere. And there's types of infrared light that also don't pass through the atmosphere. They get absorbed in the atmosphere. And this figure shows the different parts of the atmosphere where these different types of light are absorbed. For example, some of the types of infrared light that don't make it all the way to the surface, see that there's the type that does make it all the way to the surface, but these types over here that don't, well, they make it all the way down to the height where jets fly at 10 kilometers or 30,000 feet, right? And that is up in the stratosphere. On the other hand, the higher energy, because higher energy goes in this direction, so energy gets greater in this direction, and energy decreases in this direction, and that's the energy of the light, the energy that that wave carries, because different wavelengths of light carry different amounts of energy. Okay, and by the way, wavelength increases in this direction, so wavelength goes up as energy goes down, and wavelength goes down as energy goes up, right? So shorter wavelength light, or see, that should be a down, shorter wavelength light, like ultraviolet, X-rays, and gamma rays, well, those all have higher energy. Those are the harmful types of light, from a biological perspective. They're really intense light. Well, all the more intense ultraviolet light than the light that makes it to the surface gets absorbed way up in the mesosphere. And we'll be talking more about the details of Earth's atmosphere in a later chapter. But we got an energy getting absorbed up there in the upper atmosphere, way higher than planes fly. We got ultraviolet light, or excuse me, infrared light getting absorbed in the atmosphere, in the stratosphere where planes do fly. We have even higher parts of the atmosphere, the thermosphere, where we have really long radio waves getting absorbed. All right, so different types of light get absorbed in different places. And by the way, the really harmful X-rays and gamma rays, because they're so high energy, they make it almost all the way down to the stratosphere. Okay, unlike some of the ultraviolet light. Notice there's one other type of light that actually makes it to the ground, and that is certain types of radio waves. That allows for radio astronomy. We can build big dishes to look at radio waves that come from outer space. There are different sources of radio waves from space. Certain types of gases create radio waves. Certain types of very quickly accelerating electrons create radio waves. So we have cases of radio waves getting created from certain phenomena in space, and we can observe that directly at the surface of Earth. But a lot of types of light that astronomers are interested in, whether it's infrared light or the ultraviolet light that we saw the visual of the sun in ultraviolet, those have to be done with satellite-based telescopes. We have to actually put telescopes outside of our atmosphere to observe that type of light. So it's so important for astronomers to have specialized satellites for observing light that just doesn't make it to the surface of Earth. Okay, but we do a lot with our optical window with visible light and building big telescopes that use mirrors and so on down on the ground. Okay, all right, so hopefully that makes sense in terms of the EM spectrum, the light spectrum, and the different types of light that absorb at different layers of the atmosphere, and why astronomers need to build telescopes to go up and actually look at certain types of light. And sometimes we build telescopes outside of the atmosphere to look at visible light, just so we can get rid of the blurring effects of the atmosphere. That's what we do with, like, say, the Hubble telescope, primarily still looking at visible light, but it's better to put it in space anyway. Okay, all right. So lots of different types of light, important information about wavelength and energy. A lot to unpack here, okay? All applying to what light gets here to Earth. All right, so when we do put those satellites into outer space, say in an orbit around Earth, so completely out of our atmosphere, we can look at, say, X-rays that come from throughout the galaxy. This is a kind of a composite image where the galactic disk is shown here, and we can see high energy X-rays coming from the center of the galaxy. The higher energy is the blue X-rays, and again, these are color coded because X-rays are definitely invisible to the human eye. And here we have lower energy X-rays, which are still relatively high compared to visible light, right? But we have lower energy X-rays shown in red, coming from particular gas phenomenon in our local part of the galaxy, right? So we have, the very active galactic center producing really high energy X-rays. We have kind of intermediate level X-rays happening from, supernova and so on near the galactic center. Lots of interesting phenomena. Okay. All right. So now we're going to continue with another law about light. And yes, we do have a lot of laws in this chapter, right? A lot of equations to relate things. And I think it just kind of applies this idea that this is, after all, a crash course in all of these physical laws that you need to understand to talk about how it applies to astronomy, how light applies to astronomy. All right. Well, this right here shows the relationship between intensity, which here is given as an arbitrary unit, just a relative unit instead of the exact unit I gave you before, which was watts per square meter. Here it's more like, let's just compare between different temperatures. All right. And by the way, the different curves are different temperatures, all measured in Kelvin, the typical scientific unit of temperature. Okay. And on the horizontal axis is wavelength, the wavelength of the light, right? Because light is a wave. So here's the idea. There's two laws represented here. One is called Wiens Law. Okay, so Wiens Law. And Wiens Law tells us that different temperature objects produce different colored light. And this is an amazing phenomenon. Now, this only applies to solid objects. It doesn't apply to gases. Wiens Law does not apply to gases. It applies to stars, because stars are so compact that they act like a solid. It applies to like a glowing hot piece of metal. It applies to a person, all right? People produce light. We produce infrared light, which is, lower energy, longer wavelength. So let's see, all right? So if we have some temperatures that a person wouldn't be glowing at, but a very hot piece of metal or a star would be glowing at, we see that any object that has a temperature of 6,000 Kelvin is going to produce blue light as its peak wavelength, okay? Any object, like a star that is glowing at a temperature of 5,000 Kelvin, is going to produce green light as its peak wavelength. Any object that is glowing at 4,000 Kelvin is going to produce yellow light as its peak wavelength, and so on, okay? All the way down to 3,000, which is producing basically red light as its peak wavelength. All right, and we have the visible light rainbow overlaid on this information. Now, the interesting thing about this is that we got these, these different curves, and the colors, I guess I should say that they don't exactly match up. So I was saying, blue light for 6,000 because the curve is actually shown as blue, right? It's actually a blue curve, but we can see it actually, it's right in the middle of the visible spectrum. So it's I'm not entirely happy with this figure. I wish these curves actually matched up with the exact colors, because this one here should be more red. This first one that's shown as blue should actually be white. And the reason it should be white is because the peak wavelength is right in the middle of the visible spectrum. And since it's right in the middle of the visible spectrum, there's just as much of this side of the rainbow, which is by the way, the rainbow consists of, we have going from the right side to the left side, we have red, orange, yellow, green, blue, indigo, violet. All right, so this is all the colors of the rainbow in chunks. So red, orange, yellow, green, blue, indigo, violet, all shown here. So you can see the red, the orange, the yellow, the green, the blue, the indigo, and the violet. Okay, so we say the rainbow has Roy G. Biv. Those are all the colors of the rainbow. Well, right in the middle, if you have a peak wavelength that corresponds to green, it would appear white because there's just as much of the red, orange, and yellow as there is of the blue, indigo, and violet. So when you composite all those colors together, you overlay them on top of each other, it appears white because it's an equal amount of one side of the rainbow as the other. Okay, so that's white light, and our sun produces white light. That's why the sun looks white in outer space. It looks yellow here on the surface of Earth because some of the ultraviolet side, the bluer side, got absorbed a bit. The same reason that the sky is blue is the reason that the sun looks yellow up in the blue sky, because the blue light gets scattered, making the sky look blue, leaving the sun more yellow than white. Okay? Now here's the thing. That's great, right? That's that means that this curve should really be more white. This one that is colored green should actually be more of a red color, all right? In terms of the peak wavelength. But you don't just need to look at this figure to know the colors. You can actually use an equation. And Wiens Law says that the maximum wavelength, okay, because after all, the horizontal axis is wavelength, and each of these little dots is the maximum. Each of the ones I've circled now and I'm putting a little bullseye in the center of. Each of those values can be found with the following formula. 3 times 10 to the 6, and this is measured in nanometers per Kelvin, all right, over the temperature of the object in Kelvin, okay? So that means you can find the peak wavelength in nanometers, right? So the output of this equation is in nanometers, right? Every time you use this equation, you're going to get a value in nanometers, which is atypical. Most equations in physics and astronomy, they're in base units. So if you plug the values in, the output you're going to get is going to be in meters. But this one, the output is in nanometers because we typically talk about light in nanometers, especially visible light. But when you use this formula, and you just plug in the temperature in Kelvin right here, then what you'll get is the peak wavelength. So if you know the temperature of an object, for example, the temperature of the object is 5,432 Kelvin or something, well, you just plug that number into this equation, and then you find the peak wavelength that particular temperature solid object outputs. That's Wiens Law, all right? And that's the equation for Wiens Law. But notice that there's another bit of information shown on this graph, because in addition to cooler things producing more red light output, we also see that cooler things have a curve that doesn't get as high, right? See how each subsequent curve is lower as we go down in temperature? Or we think about each hotter object, like the 6,000 Kelvin temperature object, having the highest peak, which is also the peak that corresponds to white, because it's in the middle of the visible spectrum. Well, that means there must be a relationship between intensity and wavelength, okay? Or I should say intensity and temperature. And that is actually called the Stefan-Boltzmann law. Okay, so we're going to zoom out a bit, and I'm going to write it down here. So the Stefan, which is, I believe it's, no, it is not pH, it's F. So Stefan-Boltzmann. All right, two N's on Boltzmann law says that the the flux, all right, and the flux here is actually the same units of intensity, but F for flux, and I'll clarify that in just a second, is equal to some constant called the Stefan-Boltzmann constant times the temperature to the fourth power. All right, so since it's the fourth power, that means that the flux goes up very quickly, all right? And the flux here refers to an energy per time per area, or just watts per square meter, okay? So flux has the same units as the variable I that I gave you before, all right? So flux is just watts per square meter, right? It's just power per area. And that constant, the Stefan-Boltzmann constant, is a particular constant of the universe that has been experimentally determined, and it's been determined to be 5.67 times 10 to the negative 8. Okay, and we won't worry about the units, but 5.67 times 10 to the negative 8. All right, so that means that if you know the temperature in Kelvin, and you just plug in this constant, then you can find exactly how much energy that object is outputting per time per square meter. So how much power per area that object is outputting. Okay, so we've got the idea that as temperature goes up, we get a lot higher intensity light, and as temperature goes up, the peak wavelength becomes shorter and shorter, which means it becomes bluer and bluer until eventually it's so blue it's ultraviolet. All right, so those are the two laws, Wiens Law and the Stefan-Boltzmann law, all captured in this figure. Okay, so more laws, more equations, but let's then talk about what we do with this information. Well, one thing is astronomers, if they need to use these equations and really help them to create images like the one we saw of the galaxy in ultraviolet, or X-ray, excuse me, and the one we saw of the sun in ultraviolet, we need to be able to split light into its components. And we do that with a prism and some other ways. We can use different techniques. But the idea is if you take white light, like the light produced from our sun, all right, or just any light that has what's called a continuous spectrum, all right, and all of these are continuous spectrum. Why would I say that all of these are continuous, or spectra, because it's plural? Why would I say that all of these are continuous spectra? Because they don't just have one peak, right? It's not like there's just like one straight bar that corresponds to one wavelength. There's a big curve, right? Yes, the curves vary in shape and height, but they all are curves. That means they're all continuous spectra. And all stars create continuous spectra. All planets create continuous spectra. All solid objects create continuous spectra. Turns out gases don't, especially atomic gases, but we'll come back to that. All right, but that means that they're all essentially white light in one form or another. They might be more blue or more red, but they all are white, in other words, composed of many colors. So you take that type of many color light called white light, you shine it through a prism, and it splits apart. It splits apart due to variable diffraction, which we won't get into the physics of. We're already covering enough here after all. But variable diffraction basically says that different colors of light bend at different amounts in certain materials, like glass, for example. And that means that the red light bends the least, the blue light or the violet light bends the most, and the effect is that they get separated. You take white light and you produce a rainbow, okay? And this is done scientifically, experimentally, all the time, in one form or another. Scientists take white light, continuous spectrum light, and they split it into its components. Okay. Now, when we do that, then we can quantify the particular quantities of, say, visible light. And it turns out that visible light varies in nanometers from 400 nanometers. So this would be 400 times 10 to the negative 9 meters. That's the wavelength of blue. And that's really violet, but the far end of the rainbow, the most violet blue light that we can see, all the way up to 700 times 10 to the negative 9, because these are all nanometers. meters, right? And that would correspond to the wavelength of red light, the reddest light that we can visibly see. And then everything afterwards is shown as black here because it becomes invisible to the human eye. All right, so this is actually what we can see, right? These, I'll zoom in on this. You can kind of see that, these are like the bands of colors that we, as our eyes, can individually discern. Okay, that's the visible spectrum, right? Splitting it apart with something like a prism. Now, if we do that in a very detailed way, we can see that the continuous spectrum, the white light from the sun, actually has little gaps in it. So the spectrum isn't perfect. There are little sections that are black that are missing from the spectrum. There's a lot of them here in the green. There's some missing in the yellow. There's a big thing missing in the red. We've got a lot of missing colors in the blue. What's going on there? Why are there little black missing parts of what should be the continuous spectrum? Well, we say that these are absorption lines. All the little black lines are absorption lines, and they have to do to gases in the atmosphere of the sun, in the solar atmosphere, that absorb light. So that means that the sun's surface is producing all the colors of visible light, but some of that light never makes it into outer space to travel to Earth. It gets absorbed in the atmosphere above the surface of the sun, the sort of the solid part of the sun, the super hot surface, the plasma surface of the sun. Above it are gaseous, non-plasma gases and atmosphere of sorts that absorbs a lot of particular wavelengths of light. And we can tell exactly what wavelengths are getting absorbed due to the little missing bands. So that's interesting, right? So what does that tell us? What are these little missing bands in the otherwise continuous rainbow spectrum of the sun? What do they tell us, right? Are they just, random? Like, why are those particular colors missing? Well, they're missing because they correspond to particular elements, particular types of atoms, all right? So for example, some of the bands that are missing in the otherwise continuous spectrum of the sun correspond to the elements of sodium, hydrogen, calcium, and mercury. And when I say elements, these are like elements on the periodic table of elements. These are atoms, particular types of atoms, all right? So how do we know that? Well, if we look at a true continuous spectrum and compare it to these emission spectra, because there's more than one, of sodium, hydrogen, calcium, and mercury. And just examples, right? There's a lot more elements than these four, of course. We can see that sodium produces, a bright yellow band, another yellow band, couple more. It produces some sort of bluish green bands, and it produces an orange band. All right, that's particular of sodium. Hydrogen, on the other hand, doesn't produce anything in the yellow and orange. It just produces a greenish blue and a couple of violet bands. All right, now that is the atomic fingerprint of these different atoms, hydrogen and sodium in particular, the two ones I just showed you. Because we know that these elements always produce these particular bands. In just a moment, we'll talk about why, but it has to do with the electrons inside the atom. It has to do with the electrons moving to different energy states within the atom relative to the atomic nucleus. Now, we could actually produce this in a laboratory, or we can even observe it in space when you have a gas that is pure sodium or pure hydrogen. If you warm that gas up, it will emit, hence the word emission, this type of spectrum. When this gas exists in the atmosphere above something like a solid object like a star, then it absorbs. So a gas can either emit or absorb depending on if the gas is by itself and getting warmed up, or if it's above something that's warm and absorbing energy, sort of blocking that energy on the way. Okay, that's why we can see absorption lines here due to particular elemental fingerprints, or we can see emission lines here, just depending on the particular how they're being produced. Okay, so this is light being produced, and it's a good time to mention that this light is being produced due to the acceleration of charged particles, the acceleration of electrons. But where? What's going on? Why are the electrons accelerating? Well, to understand that, we're going to have to talk about the atom. And I had hinted at this a few minutes ago, that we have to do a mini little crash course on the nature of atoms. And before we do so, though, it's nice to appreciate rainbows. Rainbows are beautiful, and rainbows naturally refract. So how I mentioned that the prism is an experimental technique? Well, early scientists like Newton were inspired to build prisms out of glass because they saw refraction happening naturally in the atmosphere. And it happens due to water droplets. So water droplets do that same variable refraction. So then they bend different colors of light, or different wavelengths of light, different amounts, and thus naturally split white sunlight into a rainbow. Right? So this is a natural phenomenon, and it certainly was an inspiration for early scientists. Okay, so let's understand the atom, because the atom is going to allow us to understand emission spectra and also absorption spectra or absorption lines. Okay, so the atom was first discovered, sort of, you could say, in 1911 due to experiments by a scientist named Rutherford. And in those experiments, he showed that the atom consists, and him and his team, of a very dense atomic nucleus, which is a proton, and some number of electrons depending on the element. Okay, so these are the electrons. All right, not too important to this course, but electrons carry negative charge, protons carry positive charge. That makes the atom neutral unless it's an ion, but all atoms are naturally neutral unless they've been ionized. And there's lots of different types of atoms. Okay, here is the most common atom in the universe, the hydrogen atom. It was produced in the Big Bang more than anything else. It consists of a single proton and a single electron. The second most common element, and therefore atom in the universe, is the helium atom. It has 2 neutrons. Notice there's no neutrons in the proton, and 2 protons and 2 electrons. Okay? The fact that it has neutrons is kind of interesting, or the fact that the proton doesn't have neutrons is maybe even more so interesting. It is possible for hydrogen atoms to have a neutron. That creates something called deuterium. This creates heavy water, by the way, if you combine deuterium with oxygen. And this is what's called an isotope of hydrogen, because basic hydrogen always has just the 1 proton and the 1 electron, but it's possible, although a lot less common, to have the atomic nucleus consist of 1 proton and 1 neutron, and still that 1 electron. You even have something called tritium, which is incredibly rare, that has 2 neutrons, so 2 neutrons and an N, and a single proton, and still a single electron. Notice that the electron's always single, even with the extra neutrons. That's because the electron balances out the proton in terms of charge. It doesn't care about how many neutrons there are because neutrons are neutral. They don't have charge, okay? And understanding why neutrons don't have charge, you have to get into talking about quarks, which are subatomic particles, and certainly outside the scope of this course. But interesting thing about the atom is it's very small. So for example, the helium atom has an atomic radius of about 10 to the negative 10 meters. That's quite a bit smaller than the wavelength of visible light. Remember how visible light was on the order of, say, 500 times 10 to the negative 9 meters, which we could rewrite as 5 times 10 to the negative 7 meters, if we just move our decimal point from here. Well, that means that atoms are about 1,000 times smaller than light. That's kind of incredible if you think about it, right? Because you think about light being, so small that it's a, building block of the universe, but atoms are much smaller, okay? At least visible light is much larger than atoms. Okay, so we've got this idea that that's what atoms look like, and it was discovered due to these early experiments about basically blasting something called alpha particles, which themselves are ionized helium atoms, onto a thin gold foil, which are massive, basically massive atoms, which led to this experiment being possible. So okay, that an atom has protons and it has electrons. That's really what we care about. Okay, now at this time, after 1911, as we go into the 1920s and 1930s, so 20s to the 30s, we have a couple of scientists, among others, including Einstein, that realize that there is a big story being told here. One of them, Max Planck, had actually been building off of Wiens Law and understanding that to make Wiens Law work, we couldn't treat light as just a particle. We actually had to also treat light as, we couldn't treat light as just a wave. We had to also treat light as a particle. And he came up with something called Planck's constant, which is 6.626 times 10 to the negative 34 joule seconds. All right, and this constant allowed him to quantize light itself. And that's why you often hear about this field of study called quantum mechanics, because it was all about taking the universe and breaking it into little chunks that were the smallest chunks that could theoretically exist. And in fact, that's what the atom does as well, because we say that the atom is built of protons and electrons. Those are the smallest chunks that exist. We've since discovered that protons are actually composed of smaller chunks, but the electron is a pure particle. You cannot split the electron apart. So that's the idea of quantum. Quantum, it means steps. Quantized means that the universe exists in discrete steps, that if you zoom in enough at the very submicroscopic level, the universe isn't just continuous. It's broken into little pieces. Quanta, thus quantum mechanics, the field of study, quantum mechanics. But this is relevant to our discussion of crash course and, of radiation and emission and light and all this, because when we're looking at the atom and understanding that it's quantized, we come up with a model that electrons can jump between certain energy levels within the atom. Notice the word certain energy levels. So that means that the electron can't just go wherever it wants. We can't say move the electron up a little bit. We have to move the electron up to a well-defined sort of track. That means that there are places where the electron can exist relative at a particular distance from the proton, from the nucleus, and there's places where the electron cannot exist that are forbidden. Okay, so that's what Bohr discovered in conjunction with Planck. All right, that's the big idea. And that's going to lead to this idea that we have fingerprints. Because if the universe is quantized in discrete chunks, that means that certain elements like sodium and hydrogen and calcium and mercury can only produce certain types of light, which is amazing because it allows us to identify those elements, which, I mean, you can just imagine how helpful that is. We can identify particular elements. Okay, so if the universe is quantized, electrons can only jump between particular energy levels. Okay, what does that look like? Well, imagine we have an energy level here, n equals 1. That's the lowest energy level. The electron cannot physically get closer to the nucleus. It just can't. It will never happen. Then we have n equals 2. That's the next higher energy level. N equals 3, and so on, 4 and 5. Okay, so then we can have our electron shown here. Here's our electron, and it can jump between, say, this n equals 3 state down to the n equals 2 state. That's this jump shown here, okay? And that will produce a red spectral line. On the other hand, it could jump all the way from the n equals 4 state down to n equals 2, which would be this jump here, and it will produce blue-green, a different color. Why is that? Well, because this one has a long wavelength, which means low energy, so low energy. The blue has a shorter wavelength, which means high energy. Well, that makes sense because the bigger jump is the higher energy, which is the shorter wavelength. The smaller jump is the lower wavelength, which is the longer, or lower energy, which is the longer wavelength. Okay, so this idea of quantized energy jumps, energy states of the electron around the atomic nucleus corresponds to particular colors and their relationship to high energy, low energy, and corresponding wavelength. Right? Now we call these orbits. They're not orbits like planets because, like I said, they're more like tracks. They're also more like standing waves, like waves on a string. But no matter how we think about them, because I think there's no macroscopic analogy for this unbelievably small world, there's nothing in between. The electron cannot exist between these different electron orbits. It is absolutely physically forbidden. It cannot happen. That's quantum mechanics. All right? So that leads to a particular series of light. So for example, the early discoveries were named after the people who discovered them. So the Lyman series, the Balmer series, the Paschen series, and the Brackett series. These were all the scientists and their teams that discovered these particular series that all correspond to hydrogen, because that was the most abundant and easily worked with element to do these experiments at the turn of the 20th century. So the point being is that they correspond to these particular sections of light. And some of them were visible. For the most famously, the Balmer series actually corresponds to visible light, whereas the Paschen series corresponds to infrared light. So you have to use, you can't see it with the naked eye, right? Lyman series is mostly an ultraviolet section of different lights, all right? Different particular discrete, bands of light, that fingerprint of the element. All right, so when we were looking at hydrogen back here, we were actually, what we're looking at is the Balmer series, because we're just showing hydrogen within the visible spectrum. All of this is just the visible. So we're actually, in fact, seeing the Balmer series. Okay, we did call it back then that slide, but now we can, say that it is, in fact, the Balmer series. Although one part of the Balmer series, this longest one, you might guess is not visible because it's so long, and indeed it's not. This one would be ultraviolet. Okay. All right, so most of the Balmer series is visible. That's the idea. That's the idea of the fingerprint of elements. And to bring it back together, okay, so we have continuous spectra, like the sun, because solid objects produce continuous spectra. Then you might be like, wait, why don't they? Why do they? That's because they're producing light in lots of different ways. Because these electrons jumping up and down, that's a form of acceleration, okay? Because the electron is stopping and starting essentially as it goes between these different quantum states, all right? So that's how we produce light. Now, the thing is that you can produce light through other ways. You can have molecules that jiggle and bounce against each other. All of those create a whole range of different colored lights. And that's why any large solid object produces a continuous spectra, all right, spectrum. Now, if you take that spectrum and you have it pass through a cloud of gas, then you have the absorption lines, all right, the dark lines, which are, absorption lines. On the other hand, if you were looking from the side at this gas, right? So if you're over here, the viewer, think of this as an eyeball, and you're viewing the gas from the side, so the sun was not behind your line of sight, then you would see the gas glowing because it's picking up energy from the sun, and it would be producing bright line spectrums, emission spectrums, because all the electrons within the atoms within that gas would be jumping up to higher energy levels where they don't stay. It's an important idea. When the electrons jump to a higher energy level, they don't stay there forever. They usually stay there for a fraction of a second, some millionth of a second or something, and then they go back down. And when they go back down to the lower energy level, that's when they emit light. Okay? So they absorb energy, which causes the electron to jump up. When the electron relaxes and returns down to the lower energy level, light is produced every time. Okay? And so then we got the bright line spectra. All right? So we see now how understanding the atom basically leads us to the two really important things in astronomy: absorption lines and emission lines, okay? And then understanding the relationship with Wiens Law helps us understand that different color objects correspond to different temperatures, which is continuous spectrum. So hopefully this slide brings together a lot of complicated ideas that I've been presenting over the last few minutes. All right, so the very last thing I'm going to leave you with is the Doppler effect. And I'll give you one more equation for the Doppler effect. Now, this is not related to atoms anymore, so this is going to be our last idea that doesn't apply to atoms. And what we're talking about here is that when light sources like continuous spectra or a hot gas, so emission spectra, when they're moving towards us or away from us, the wavelength gets changed. And that's the Doppler effect. Now, the Doppler effect applies to sound too. So if you have a source of sound, like the siren on an ambulance, when it's coming towards you, it's a higher pitch, and when it's moving away from you, it's a lower pitch. That's because the shorter wavelength, when it's moving towards you, creates a high pitch, which your ear perceives as high pitch, and the longer wavelength, when the source is moving away from you, corresponds to lower pitch. So it's like, right? High, low. Okay, so that's sound and the Doppler effect, very common phenomenon. But it applies to light too. Since light is a wave, if a light source, and again, we got these nicely understood light sources, the big three, continuous, spectra, and absorption. When any one of those light sources move towards you or away from you, they're going to get shifted in terms of their wavelength. If the light is moving towards you, so towards observer A, it gets shifted towards the blue, and we say it is a blue shift. Okay, because the wavelengths get shorter. Shorter light is bluer. Now, it's not necessarily going to become blue. Maybe it becomes ultraviolet, but it moves in the blue direction. If something is moving away from you, we say it's a red shift, all right? So something is moving away, longer wavelength, so the wavelength has gotten longer, that's a red shift. So blue shift is any source of light moving towards an observer. Observer usually means Earth. Red shift would be anything moving away from an observer, like Earth, okay? You can also have things moving away at angles, and you got to kind of figure what's going on, because you can only discern the component of motion that's either directly towards you or directly away from you. All right. So in other words, if something's moving side to side, then the wavelength is unchanged. That would be like so if something is just moving past you, you can't tell, because there is going to be no discernible Doppler effect. It has to be either at least partially moving towards you or partially moving away from you. The equation for this applies to the speed of light and the change in wavelength. Okay, so we got the change in wavelength due to the motion divided by the original wavelength, like say the original wavelength of one particular energy transition, or just some well-known wavelength. There are famous wavelengths in astronomy. We'll talk about some in later chapters, okay? Well, that's going to be equal then to the velocity of the source divided by the speed of light, okay? So this equation is then usually used to solve for V. So we cross multiply by c, and then we can actually solve for the velocity of the source, either towards us or away from us, based on the change in the wavelength that we observe. Now you might be like, well, how do you know the wavelength has changed? Because we look at the fingerprint of the element, and we compare it to a known element. So if we can tell it's hydrogen, but the hydrogen isn't exactly where we expected it to be, so for example, if we looked, I'm going to show you, and we saw that all the hydrogen lines were shifted towards this direction. So they're all the same lines, clearly, based on their spacing. but they're all shifted in this direction towards red, right? Because, towards the red direction, then we know that that source is moving away from us. That hydrogen source is moving away from us. So we it's really this combination of understanding atoms, understanding the atomic fingerprint of elements, and then relating that to relative motion. Really amazing science going on here with our understanding of light, and really the backbone of what astronomers do and how they gather data. Okay, well, I know that was a lot to take in, but I hope this lecture was interesting and certainly, a building block that's going to help us understand, future astronomical ideas that we present in the next few chapters. Thank you so much for watching.